All right. Morning, morning, morning. Happy Wednesday. I wanted to try to take today and recap a little bit of yesterday's stuff because I know you were at home when we did it. And give us a chance to really just kind of work on the power rule today. Now we have our first initial shortcut, and it's the biggest one for sure. Every other kind of algorithm you're going to learn this year is all, in general, based around power rule stuff when we're dealing with most of our functions. And it kind of goes back to some of the examples that we did kind of leading up to it. So I just wanted to remind you maybe of what some of those results were and see if you can, oh, that's an X, sorry, F prime of X. See if you could remind us of where I am getting all of these answers from so that we can kind of recreate what we wrote down and making sure that we feel like we've got a pretty good sense of how to do it. All right, so let's just look at like those. Yeah, no.
So
tell me something.
So you multiply the exponent by the x, which is the number?
It doesn't have to be a whole number. What's that number called in front of x? Coefficient. There we go. So we take the exponent, whatever it was. What do we do? Multiply. Okay, so we multiply by the coefficient.
And then you take one away from the you decrease it.
But not the coefficient, the exponent.
I
think that's what you meant. Yeah, and that's the power rule. Like that's really it. Now, like the thing that we have to remember is that if we do just have like a constant, the derivative of that is always just 0. Now, it still holds true because this is 6x to the 0, right? That's what 6 is. And so take the exponent, multiply it by 6, 0. 0 times anything is just going to stay 0. So it still holds true, but you don't have to write it like that. We can just kind of jump right to 0. And eventually, and like by eventually, I mean right now, we're not going to actually write 0. That would just be silly. We'll just call that negative 9x squared plus 24x cubed. But that's the idea, is you take the exponent, multiply it in to whatever the coefficient is, and decrease the exponent by 1. But it has to look like these in order to do that. And whether they're positive numbers, negative numbers, fractions, it all works, which is so nice. And it goes back, like I could prove it to you with the limits, but it's there. And you can see that all the examples that we did, if you look back at every one of those limits, it's going to hold true, which is really, really nice. And so if we've got that, right, and so we kind of like wrote it down over here, I think, yesterday. We said, all right, if we've got some function, and it's, c times x to the n, right? Some constant, some coefficient, times x to some power, whatever that is. And you can just go term by term by term. Like I'm not taking the derivative of the whole thing all at once. I'm just going one term at a time. Then the derivative, so then f prime of x, we take that coefficient, you multiply it by the exponent, and you decrease the exponent by 1. Like, and that's the power rule. Okay, that's the power rule. But it has to be written as a power for that to work. Okay? And that's just x to some number. That if it's got, radicals in it, or if it's rational, right? It's, 5 over x to the 4th. That's not written the way we want. We just want to make sure that we do that. Okay? But now we can use it all the time, over and over and over again, and we don't have to use limits in order to find derivatives. Okay, unless they ask us to, right? They say use the limit definition. All right, I'll go back to the old school with the x plus h's. And the limit is h goes to 0, but if it just says find the derivative, do it as quickly as you possibly can. It's a really good way to do that. Okay, so we cool with that, right? Drop it in front, multiply together, decrease by 1. The other thing that comes up here in the bottom of page 130 that we just haven't talked about yet is a different style of notation. Okay, this whole f of x and f prime of x setup right here, that notation right there, that's our boy Isaac Newton. Okay, that was his idea. And as nice as that is, it does not allow us to do some of the more interesting things with derivatives as we kind of move on in calculus. And so across the way, kind of at the same time, our other boy, Leibniz, Gottfried Leibniz, had a different idea on how we wanted to write these down. And so what he did is he wanted to make sure that he gave us a chance to connect kind of the old ideas to the new ideas. Remembering that when we talk about slope of a tangent line, that we're really talking about slope, which is, changing y. And so what he did is he said, well, we're getting to the point where this is 0 and so is this, right? We're going to let the distance become 0. They're just going to go and become one another. And so he decided to use slightly different notation and say, not delta y over delta x, but he called it dy over dx. Of course, delta starts with d, and so it's the same kind of idea. But like this was the slope of the secant line in his mind. This was the slope of the tangent line. And he said, well, if I use a slightly different notation to talk about what are called differentials, derivatives and differentials are very closely related to one another. The differential meaning I'm going to take the distance between them and I'm going to make that difference, differential, difference, I'm going to make that null, right? And once he wrote that down, he said, oh, that's kind of a nice notation that maybe I can start using more frequently. Maybe that in my mind is something that I can write down as notation to represent the derivative. And so what he did is he said, you know what, I'm going to name that. I'm going to call this the derivative of y. And that's kind of what that dy is on top. That's how I'll say that out loud, the derivative of y. But this whole dx thing on the bottom was really an opportunity for him to say, all right, when I write it down as f of x and f prime of x, I know what my input is. It's going to be an x. Versus like that s of t or h of m or whatever letters we decide to use, we want to know what that independent variable is that we're taking the derivative with respect to. Now, what am I actually taking the derivative of? Well, y. But if it's y and not f of x, I don't know what that input's going to be. And so when we read this part out loud, we're actually going to read it as the derivative of y with respect that it's not just some y and I don't know what's going on with it. I know what that independent variable is going to be, and it's going to be x. And so that's what this is right here. This, without the y, we just read it as the derivative with respect to x. And it's actually a much more common with respect. It's actually a much more common notation in calculus to use this derivative with respect to x, or the derivative of y with respect to x, than it is to use f primes or d primes or something like that. And you're going to see why, because although it's not all right, it came from a fraction, right? It came from slope fractions. But in his mind, he was like, well, you know what? I can use this almost as an operator, like a functional operator that says, I'm going to do something to this function. I'm going to take the derivative. And as much as it looks like a fraction, and we actually manipulate it almost like a fraction as we get to the end of Calc A and into Calc B and Calc C, we'll split apart the dy and the dx. I want to multiply both sides by dx. Well, I'm not really multiplying. It's like this whole weird gray area with just a notational kind of side of things. But it is a very common way to write things down. And so I'm going to start intermixing that into the discussions that we have. Instead of writing f prime, you might see me write the derivative with respect to x of f of x instead. And that's kind of what they're doing here. They're saying, okay, like that right there is whatever my function is. The derivative with respect to x of x to the m. Oh, drop the exponent in front, decrease the power by 1. And that's the original power rule. And that, it just works with constants as well. We just multiply those in. The constant in there is just a 1 right now, which is why you're not seeing that. But that's kind of the beginning of the power rule. And that's a lot of words to say for a very simple idea. The derivative of y with respect to x, the derivative of y with respect to x, 8 words. Okay, we're mathematicians. We're lazy when we say stuff out loud. So we are actually going to feel okay reading this out loud in an even simpler way. dy dx. I don't even say over. Like, I don't even mention that it's a fraction. I just say dy dx. Or, in this case, d dx. Okay? Knowing what I really mean is the derivative of something and with respect to x. Right? So if our independent variable was like t, right, for time, it would be dy dt or ddt. Like, we're actually going to change that letter on the bottom to represent whatever that variable is inside. Now, most of the time, it's just x. So we don't have to worry too much about it. But when we get to projectile motion and velocity and acceleration, stuff like that, and gravity acting on objects and stuff, it's going to be with respect to time. That's what's going to be changing a lot of time. So we'll see a lot of ddt's and dy dt's. But I'm not going to say it out loud too much, the derivative of y with respect to x. You're going to hear me say dy dx a lot. But those two mean the same thing. F prime of x, dy dx, they are one and the same. It's just two different guys doing their thing separately, right? This is Leibniz. Leibniz. In case you want to check him out. Gottfried Leibniz. I don't know why I said that like he was English. Gottfried Leibniz! There we go. That's the German. It's a little better. Okay. But intermix those and start getting comfortable using both. I think that'll help us out. And I'll try to do that today a little bit. Okay, so just some notational stuff. Yeah, Anna. So in this case, there wasn't one. Like right in here, it's just a 1. So yeah, there's a 1 right here, but I just didn't bother writing it. But absolutely, if there is a coefficient, we will always multiply that by the exponent and then just decrease that exponent. And what I wanted to do was really just give you a sense of confidence in being able to do that on functions that are simpler to start. So when I turned the next page, I saw functions that were like really complicated right away. It just didn't look ready to go yet. And so what I did last night, once I was doing that, as I said, all right, we need to pause for a second. We are going to need to make sure that we can practice this well first. And so what I did is I designed a homework 2.3, which we're going to do right now. Okay. Now this is not in your guided notes. So you might want to find a separate place to, and it won't take very long, to quickly work through these 5 derivatives. Using only the power rule. Okay. And we're going to do the same thing every time, but when we get to something like 4, 5, where things just look a little different, we'll talk about what we're going to want to do with some of those other ones that maybe aren't really polynomials, right? They're polynomial types, but 1, 2, and 3 are polynomials because their exponents are all non-negative and they're all whole numbers. They're all natural numbers, if you will. But then 4, you get some negative exponents, and 5, you get these rational exponents. Like, what does that do to us? So I'm just separating that so I can write down some answers as we go. But when you're writing this down, wherever you decide to, maybe just kind of in the next page in your notebook, make sure you write down the original function first. Okay, and folks at home, you guys can do the same thing. Okay, this is homework 2.3, and it's up on Canvas, ready to go, so you can jump on, or you can just look up here with us. That's why I made it nice and big. But just find the derivative right away for each one. So find f prime. Find g prime. Find h prime. Find a prime. And hey, why not? Let's find dy dx, which is the same thing as y prime. And just use a power law. Okay? Take the exponent, drop it in front, multiply it by whatever the coefficient is, and decrease the exponent by 1. And just go one term at a time. And that's what's so nice about these functions written this way. If it's just term by term by term, that's how I can do my derivative. Not all at once, but one little piece at a time. Now let's see how you do. Just be sure to write the original function so then we go back to look at this later this week. And then when we get back into the break, like I might have said, I don't know if you heard me, but we are not finishing chapter 2 this week, which means we are not taking the tests anytime this week or next week. I have made the executive decision to give you next week off completely. Okay, you deserve it. Okay, so no calculus over break. But probably the week we get back, we'll take that test at the end of the week. Okay, either Thursday or Friday. Because we'll all be back. We'll all be back together. So we will take it all at once. Either Thursday or Friday, or if we need both days, then we'll take it. I'll start getting some answers up there so you feel like you're getting it right. Or if you have questions, then you can ask them as we go. Again, I'm not putting the +0 at the end of that second one. Okay. It's there, right? The derivative of 1 is 0, but I'm not going to put a +0. It doesn't change. I'll do the third one. right? And you take away 1 from a negative number, it's going to get more negative, so be careful there, right? We want to make sure that we're subtracting 1 no matter what. And we're keeping track of signs, but we're multiplying numbers together. We want to make sure that the signs match up as best we can. And realistically, every single one of those could have been dy dx. Every single one. Okay? Or ddx of f of x. ddx of g of x. ddx of h of x. Okay, so there's definitely some varying notation that you want to familiarize yourself with. But I love like 1, 2, and 3. Man, those are just so nice. They're so easy. They're written as polynomials and life is good. There's something about 4 that I just don't love, though. Both the function itself and the derivative. What do you think might irk me a little bit about the initial setup for a of x and even the way that the derivative looks right now? What do you think? At least like what's different maybe about 4 compared to everything else? Negative exponents. Okay. And negative exponents are real, and we like them very much. It makes it easier to do this problem, but negative exponents came from rational functions, right? This is really 2 over x to the third. This is, x 1 over x squared. This is 5 over x. And that's not a polynomial function. It's written like a polynomial, but it's really rational. And so what you're going to see a lot of the times in calculus is that most of the time it's not going to start like this. It's going to start like what I said, 2 over x to the third minus, 1 over x squared plus 5 over x. That's what a of x is probably going to start with, right? It's going to look like that. Or maybe even trickier, just as 1 fraction all over x cubed. And it's going to be up to us to make some changes. But absolutely what we need to do, we have to make sure that no matter what, we are not leaving negative exponents as part of our answer. Okay? And I know I didn't specify that up here, but you're going to see that all throughout calculus. They're going to say, make sure your answers don't have any negative exponents in them. So we want to make that switch right now. Okay? So when you look at this, right, negative 6 x to the negative 4th. What is being raised to that negative power? Just x, good. Not the negative 6. And so when I decide to move things around, right, negative exponents are my clue that something's in the wrong spot, either the top of the fraction or the bottom. I got to make that switch. The negative 6 is not part of that. Okay? Only the x is being raised to that negative power, so only the x is going to make that move. Okay? So make sure that if you wrote this as your answer for a prime of x, that you come down and you separately start writing the better version, the one that they're going to do. Okay. Same thing with the 2x to the negative third. The 2 is not being raised to a negative power, so only the x moves down to the bottom of the fraction and becomes positive. Right? Minus 5 over x. And even more so, sometimes what they'll do is they'll make us do this. 1 fraction with a common denominator, which is just going to be the biggest exponent. Okay. And making sure that we can make adjustments like this. If I want everything to be over x to the 4th, well, then I better create common denominators by multiplying top and bottom by what I need to. Okay. There's definitely no negative exponents, and sometimes, even just as a single rational function, sometimes they make us go this far. Now, I think that this is a little bit extra. Like, I like this version in blue with the different separate terms. There's just no negative exponents. So sometimes they say, hey, we got to make it one rational. Do you see how that all worked out? We cool with the process there? Okay. It should be old news. It's just exponents. Okay. Now what about this one? what don't we like maybe about the results that we get in dy dx? Well, negative exponent, of course, right? So that's no good. What else, though? Yeah, we've got radicals, right? That's what fractional exponents are. And sometimes they'll say, hey, listen, fractional exponents are okay. Sometimes they'll say, you got to change it back to rational, from rational exponents to radical form, okay? And remember that fractional exponents are power over 3. Okay? This really means 3/2 and then the square root of it. Right? Now, this right here, that is -2 over x to the 2/3. Right? That's what that is right there. Right? I have to take care of the negative exponent first, but now I even have to get rid of the fraction altogether and say, okay, my power is 2, so this is x squared underneath here. But my root is 3, so it's actually a cube. But it all depends on what they ask us to do, okay? For sure, no negative exponents. Okay? But if they don't specify about those, radical versus rational setups, or if they don't specify about making one rational function, then just get rid of your negatives and be happy about it, okay? But we have to kind of do whatever they want us to. But what I'm hoping is that everything in that magenta color you were able to do pretty well. Right? You were able to apply the power rule and get to those spots. Okay, everything else from there is more just about manipulating things and making them look the way that we want. But if you can do the power rule, you're off to a really good start. Here's the end of chapter 2. Cool. Now, with our last handful or 2 of minutes here that we have left, now that we've got our feet wet with the power rule, what I want you to start being able to do is recognize that 1 through 5, that these are ready for the power rule, but it's not always going to look like this, right? The problems that they give us, the original functions that they provide to us, are sometimes written as polynomials or polynomial types, but sometimes they're not, right? Maybe they look like this to start, okay? Or maybe they look like this to start. We're going to have to make some adjustments, just like we made adjustments now to rewrite things to make them look better. We're going to do the same thing to make them ready for the power rule. Now, we're not going to get through all of these problems, but we're going to start them right now, and we'll finish them up tomorrow, okay? Any questions before we do that? Okay. Jump back into your guided notes now. I know we left off on the bottom of page 130 with our little notation conversation. Conversation. Conjunction. Here we go. Okay. Page 131. Okay, I'm skipping that little question there up at the top. Go ahead and flip the page to page 131. Don't worry about the question at the top. We're jumping right into it. Find f prime of x for each of the following functions. Okay, so as soon as I see that, I'm like, okay, I hope I can use the power rule. Did they say anything about limits? Ooh, good. No. They don't mention limits. Don't do it that way. Right? The limit definition is long and arduous, and man, it works, but it takes forever. So if they don't specify, let's use the fastest way possible, and power rule is definitely a good way to do it. But look what they kind of guide us towards right after that. Leave your answers with no negative exponents and no rational exponents, right? So I can't have a fraction in my exponents. So I got to change it back to a square root or cube root or something. And if you can, make it one rational function when you're done. So if you have any rational functions at all, make them one. Kind of like I did there at the end of that second to last one. Okay? And so I look at this first one, this top left one, and I say, okay, nice. At least I don't have to use limits. But if I want to use the power rule, I cannot jump into f prime of x. We actually have to rewrite the function itself. We're going to have to look at this first one on page 131 and say, listen, this is not looking the way that I want it to. Now, I like this one, negative 4x cubed. That's set up nice, but I don't like this. 2 over x squared is not written as a power, so I cannot use the power rule. How can we rewrite 2 over x squared so it goes coefficients, x, exponent? That's all we want every single time. Coefficient, x, exponent. Coefficient, x, exponent. Then I can use the power rule. Let's rewrite what's circled right there. 2x to the negative second. Like I said, I like a minus 4x cubed, so I'm going to keep it. But none of that is the derivative yet. That is all about rewriting the function first. Now we can do it. Now I can do f prime of x. Exponent goes in front, multiplies with the constant, gets decreased by 1. Exponent goes in front, multiplied with the constant, exponent gets decreased by 1. We are just not done yet. We cannot have any negative exponents. So let's rewrite it. Just like we turned this into that, let's rewrite this so it looks more like that. The x is the only thing being raised to that negative power, so that's the only thing that's going to move down to the bottom. And when it does, now we can use the positive version. So we got negative 4 over x minus 12x. And that looks pretty good. At least it takes care of the negatives. But, man, we do have one rational piece to this. And they really want us, if we can, to write it as a single rational function, all over x. Whatever your largest exponent is in your monomial denominators, that's your common denominator. Now, if this was like x plus 1, we'd have a lot more work ahead of us. Because it's just x, or x squared, or x cubed, all I have to do is make each fraction that big. Right? Well, this one's good. Negative 4 is good. It's already over x cubed, so I don't have to change a thing about that. But this one doesn't have any fraction part to it at all. So I know that I'm going to have to take this and multiply top and bottom by whatever I need to make the common denominator. And since there's no x at all in a denominator, I need to multiply top and bottom by x cubed. So that gets me to here, negative 12x to the. When we multiply, we add it. There's our group. Now, I really like this one, though. I really do. And it almost bothers me that they make us turn it into a single rational function, but we are kind of at the whim of what they need us to be comfortable with. So it's just good practice. So I like what's boxed in blue, but what's circled in red is what we're trying to shoot. Does any of that process not sit nicely with you, or do you feel like you totally get it and I'm on board and let's keep rolling? Because if you don't get it, now's the time to speak up. Okay, cool. So let's do the same thing here, but I've got problems, right? It's not coefficient x exponent, coefficient x exponent. It's a fraction. This is a rational function. We got to get rid of it. We have to do something to make it look more like this. So how do we do that? What do you think we could do to rewrite f of x so it looks more like a polynomial? So you could have it look like this. So 3x to the 4th. Oops. So don't write this yet because I want to see what happens when we do it. 3x to the 4th minus 3x squared minus 2x times x to the negative 1st, right? But when we do that, we're still not at a polynomial yet, right? Because we still have parentheses. But you're absolutely right. We need these because every single one of these is going to get multiplied by x to the negative 1st. So we got to keep going. Now what? How can we get rid of parentheses? Multiply things out. And by multiplying things out, we're just going to take this 3x to the fourth and multiply it by that, and this, and times that, and this times that. And when we multiply x's together, we add their exponents. Really what's going to happen is this 4 is going to become a 3. And this 2 is going to become a 1, and this 1 is going to become a 0. And what we're really seeing happening when we do that is we're dividing each of these terms one by that x. Right? When you have a don't erase it all. When you have a single denominator, whatever it is, you got a bunch of stuff being added or subtracted up top, divide each one separately. 3x cubed minus 3x minus 2. You have a single denominator, whatever it is. Just divide everything by that x, or by that x squared, or by that 3x cubed, or whatever it is that we're trying to divide by. Again, that's not the derivative, that's just a function. So let's jump in and find the derivative now that it looks like that. Well, that just got a whole lot easier. No negative exponents to start with, so that's good. 9x squared minus 7. Right, I'm not putting the plus 0 for the minus 2, but it's there. Right? The derivative of negative 2 is 0. But just by taking that 1 second and rewriting it, we're avoiding a lot of pitfalls that we could fall into in chapter 3 when I teach you what to do with fractions that maybe you just either can't divide stuff away or you just don't want to. Just like we have the power rule, we also have a quotient rule for rational numbers. Okay, we can find the derivative right away by using a nice little shortcut. But I think this way is going to be faster. This is definitely a faster way than trying the quotient rule. You'll see that. Okay, nice. All right, couple more. Let's see if we can maybe get these next two. We'll see. But obviously, this is not ready to go. This is not looking good. There is a product rule in chapter 3 as well that maybe you would use in a case like this because you don't want to multiply this stuff out. We don't know that yet, and so we're kind of stuck multiplying these three things together. We have to distribute. We got to get rid of these parentheses so it looks the way we want, but how in the heck do we do that right? And I'll write this down, but I just want to have this conversation. We got three things being multiplied together. All right, x plus 2, x plus 3, x plus 2, and then 2x. Well, how do you multiply 2 times 3 times 4? What do you do first? In your mind, when you multiply those together, what are you doing? What do you mean? So, ignore this. This doesn't exist. Do this product. How are you doing 2 times 3 times 4 in your mind right now? And then you stop and you figure out what that is, right? You do the first two first. Then what do you do? Then you do 6 times 4 and you get 24. Right? That's kind of how your mind's going to work. It doesn't matter what order you do them in. I could do 2 times 4, get 8 times 3 is 24. 3 times 4 is 12 times 2, still 24. Doesn't matter what order you decide to multiply them together, but you only really do 2 at a time. And so if I'm going to rewrite my function, not the derivative yet, but just kind of rewriting the function, I am going to multiply those first two together first. If you're going to distribute more than 2 things, you really can't do them more than 2 at a time. So we're going to multiply those together, and I'm going to simplify as I go. All right, x squared plus 2x plus 3x. So plus 5x and then plus 6. And then you do it again. Right now, like this is 6 times 4, right? So now I can just multiply these together. Okay, you give it a shot. I'm going to do the same. X cubed. There's the one. Here's a notation, just so if you're interested in using it. And that's the same as f prime. But just so you see it, why not? The derivative with respect to x of f of x is, oh man, this is kind of a lot easier. It's a polynomial. Okay, sweet. Got the coefficient, exponents and coefficients, and do my thing. Multiply, subtract one, multiply, subtract one. The derivative of 6 is 0, so I'm not writing it. But it's still there in my mind. That's going to help you out a lot in whether you take Calc 1 next year or you take an AB or BC, remembering that the derivative of a constant is 0. Definitely comes in. Just doing like a little bit of algebra there. Saved us from a lot of complicated calculus. The product rule for calculus, you got a couple things being multiplied together and you decide not to distribute. You just want to jump right to the derivative. It'll get you to the same spot. That's right. Yeah. Get you to the same spot. But I think this is easier. At least with a setup. Sinking in all right so far? Okay, cool. Let's do one more. Let's do this last one. We'll save the bottom two for mañana. Is f of x ready to go? Does that look good? You like that? What should we do? What are we going to do to this if we don't like the way it looks right now? We don't want to get to. We don't want this to be a polynomial looking kind of thing. Well, we got some stuff up top being multiplied or being added and subtracted. It's all over x of this. What are we going to do? Yeah, divide everything by x to the fifth, right? Now, maybe this is your mindset, and maybe you even decide to write it down, but here's kind of what we're doing. I'm going to take x to the third and divide it by x to the fifth, right? Then I'm going to subtract 5x squared over x to the fifth, right? That's kind of what's happening in your brain, and feel free to write that down if that helps. I'm of course, I'm cool with that. The more you write down, the easier it gets. But we're dividing away more x's than we started with, right? I have an x to the third, but I'm dividing by x to the fifth. I have an x squared, I'm dividing by x to the fifth. What's the, like algebra 1 back in the day, what's the shortcut for exponents when you divide? You subtract them, right? 3 minus 5 is negative 2. Minus 5. 2 minus 5 is negative 3. That's my function. Okay? And so if your degree on top for each of your terms is smaller than your degree on bottom, you're going to have some negative exponents once you do. Okay, cool. Oh, the derivative? Nice. Negative 2, x to the negative third, plus 15, x to the negative. Do we like that? No. You got to deal with those negative exponents, and we will do that tomorrow. Okay. So you can leave it just like that. We will pick up right from this point, because I think this is exactly what I got to in second period somehow, magically. But those first 5 problems that we kind of all did together, practicing the power rule, that's on Canvas for you to like get yourself some 5 points for it. Okay, so homework 2.3 is sitting there on Canvas for f of x, g of x, h of x, a of x, and then y. For our stuff from the beginning. So make sure that you take a photo, put it up on Canvas maybe right now or maybe later. Make sure you do that by the end of today. So I can give you some points for doing amazing stuff. Okay, go to homeroom. All right, today's Wednesday. Head off to your homeroom class. And then we'll jump right back into it tomorrow. Thanks, everybody. See y'all. Appreciate y'all. Ghost town on the Google Meet. Everybody